Hello, Chem 110. I'm here to continue our discussion of thermochemistry. This is going to be a continuation of Friday's conversation. We're going to define Hess's law and use it to determine the reaction enthalpy for a multi-step process. We're going to look at calorimetry and see how that experimental information can be used to determine the heat of a reaction. And we're going to make predictions about how a solution's temperature would change based on the enthalpy of reaction. So let's get into it. This is a slide that we saw on Friday, and we saw this balanced thermochemical equation, and we saw this heat of reaction. And we used it to figure out, how much heat was given off through a certain amount of combustion. But the topic that we're going to get at today is, how do scientists determine the delta H of reaction? So how did they determine this negative 3,120 kilojoules? And so what we're going to see in Chem 110 is 4 different ways to determine these delta H values. And so we're going to see 2 today, and then we'll see 2 on Wednesday. And the first strategy that we can take advantage of is this Hess's law. So the idea behind Hess's law is that if we know the enthalpy values for some smaller reactions that then make up a bigger reaction, we can add those together to determine our overall delta H reaction. So let's say we're interested in looking at or determining the delta H of reaction for the conversion of species A to species C. And right now, we already know how much energy it takes to go from A to B, and how much it takes to go from B to C. And so if we have our scale for increasing enthalpy, we can look at the enthalpy value for A, and then look at the change as A turns to B, and then look at that change as B goes to C. And so then hopefully it's clear then that moving from A to C would then be a combination of those 2 delta H values. And so here's just a little more commentary on how to create such an infographic as what's on the right. And it can be useful to draw those arrows sometimes to help you visualize what those numbers are telling you. And so what we can do then is just add our A to B and B to C equations and add their enthalpy values to get the enthalpy value of the reaction that we're interested in. But there you can see we have a B on each side of the arrow, and so those will just cancel out, leaving us with what we're interested in. And so this is the general strategy we're going to take for Hess's law. We have 2 examples to work through here. So first we have this reaction with aluminum, oxygen, and iron. And so we know something about these first 2 equations, but we don't know anything about equation C. But we can see that it's made up of pieces that are shown up in equations A and B. So our goal is going to be to rearrange those in some way that we can then combine to get our reaction C. And then we can combine the adjusted enthalpy values to get our enthalpy for reaction C. Okay, so let's go ahead and look at steps for that. So first, what we want to do is make sure that the products of our desired reaction, which is reaction C, show up on the product sides of the reactions above. Okay, so if we look at reaction A, it has one of the products as the aluminum oxide here, and it has aluminum oxide in the product side. So that seems good because then, these are kind of matching. But then if we look at equation B, our one product of iron, solid, is showing up in the reactant side of the equation. Okay. And so what we're going to end up having to do is flip reaction B so that our reactants and our products end up on those respective sides of the arrow. And then when we do that flipping, we're going to flip the sign on the delta H. Okay, so like I said, that reaction looks good. That reaction needs to be flipped. And so when we rewrite our kind of new reactions, we'll have A looking the same. And then now we'll have B, which is denoted with this apostrophe or prime sign, just to remind us that something did change about it from the original. And here you can see that we've reversed how it's written. And so then we're going to reverse the sign on the delta H value for it. So then our next step now is to make sure that when we combine our two equations, that we'll end up with the proper number of moles or values of coefficients so that we end up matching the desired equation. And so if you change the coefficients by multiplying or dividing by some number, you have to do that same thing to the delta H value. And so you can see here that to reaction A, we divided it by 2. It goes from 4 moles of aluminum to 2 moles and so on. And that was done so that we could match the 2 here. And so since we divided our coefficient by 2, we're going to divide our delta H by 2, which is the same as multiplying by 1/2. So we have this new adjusted delta H value for the first reaction. And now we're going to do the same thing to the second reaction. We can see here that in this reaction, we only have 1 mole of iron oxide required for the reaction to happen. Here it's written as 2, so we can divide by 2 to match. And so then again, we're just going to multiply by 1/2 and get this new adjusted delta H value. And so now we're ready to go ahead and combine our two reactions. We can see that the oxygens cancel. They're on opposite sides of the arrow and they have the same coefficients. And we end up with equation C, which was our goal. And so then to figure out its delta H of reaction, we're just going to add our 2 new delta H values, or adjusted delta H values that reflect the changes we made to the reactions. And we get that the delta H for reaction C is negative 852 kilojoules. Okay, so lots of kind of little steps to keep track of. Don't be afraid to, write these equations out over and over again and make sure that everything cancels out appropriately. Let's go ahead and look at another example. And I would like you all to give this one a try on your own first. So go ahead and pause me. Okay, good work. Thanks for giving this your best shot. Let's go ahead and go through it now. So here we have 2 reactions that we're trying to combine in order to learn something about this third reaction, reaction C. Okay, so to do this, I'm going to start by flipping reaction A. Okay. Sorry. I'm going to start by flipping reaction A, which means I'll also have to flip its delta H value. I'm going to keep reaction B the same. And so by doing this, we can see that the SO3 will cancel, And that doesn't show up in our third reaction. So kind of another way to keep track of whether you need to flip an equation or not is to see if you need to do that in order to get rid of what doesn't appear in your third reaction. And by keeping B in the same orientation, I have my sulfur, which is a reactant, still on the reactant side, my oxygen, which is a reactant, still on the reactant side also. Okay, so then that number stays the same. And so next we're going to consider our coefficients. And we would see that if we were to combine these equations together right now, all of our molecules would have a 2 in front. There's no need to multiply everything by 2. So we're just going to divide it by 1/2 so that we're able to match our 1:1:1 stoichiometry. So here we have reaction A after it's been through these 2 changes. And then its delta H value after it's been through those 2 changes. And now we're just have reaction B after its coefficients have been divided by 2. And we'll have its delta H value divided by 2. And then we'll just combine our 2 delta H's in our reactions. We'll see some of the oxygens cancel. Okay, not all of them, but some of the oxygens cancel. Our SO3s cancel, and we're left with the reaction that we were trying to make. And so then we can just add our adjusted delta H's together and get our unknown delta H that we were trying to find. So if you were able to get to that final answer on your own, great. And if not, that's okay. It's your first time seeing this. And I recommend that you work through the homework and do some practice and see what you get. So that brings us to our next topic and another way that we can determine the delta H of a reaction. And that is called calorimetry. And maybe you all are familiar with this building on campus. The forum's kind of like right behind it from how this picture is taken. This is the Calorimetry Museum on campus. So hopefully soon you'll be able to check that out and see some history. Okay. But calorimetry is an experiment where you measure the flow of heat. For those of you who speak Spanish, maybe you recognize calor as being heat. So the Latin roots there match up. Okay, and so we've already done some calorimetry stuff. When we're looking at phase changes and stuff, we were looking at heat flowing. And we had this equation, Q equals, MC delta T, where we had the amount of heat transferred, the specific heat. So this was our number that's oftentimes in like joules per gram Kelvin, or something like that. We have our mass, or just our amount of sample, and then we have our change in temperature. And so here we have a schematic of, a calorimeter that you may have made in Chem 111. It's basically just 2 styrofoam coffee cups together, and those are just meant to hold the heat inside of the reaction and not let it escape. And then you stir your liquid that's in here, and you have some reaction happening. You measure the temperature before the reaction happened and then after the reaction happened. And by measuring your change in temperature and knowing how much stuff you added into your reaction, you can determine either the heat capacity or the delta H for a reaction. And so something that I'd like to point out, for our aqueous reactions, usually we say water is part of the surroundings. So water, is the chemical that's within our container, but usually it's not the thing that's actually reacting. It's just holding the things that are reacting within itself. So we treat it as the surroundings. And So this is just referring to the Q equals MC delta T, but for the surroundings. And if we know what's happening to the surroundings, we just say it's the same amount of heat transferred, just it's flowing in different directions. So whatever is happening to the surroundings, the equal but opposite amount is happening to the system. And this might make more sense when we look at an example shortly. And so there's a video in the ebook of a coffee cup calorimetry experiment. So let's go ahead and watch this. So they start at 19 degrees Celsius, pour in some reactant, cover it to trap the heat in, and we can see that the temperature then increased to 26 degrees Celsius within the coffee cup. Okay, so let's go ahead and look at an example of a calorimetry experiment. So here, what we're going to have is some really hot, potentially molten steel. And we're dumping the steel into water. And then what we're going to do is monitor the temperature. Oh, that's a terrible thermometer, I'm sorry. Okay, but we're going to measure the temperature of the water. So maybe it starts at room temperature. And then as the hot steel is added in, the temperature is going to go up. And so we're going to use this principle where Q absorbed is equal to Q released. Okay. So another way to write this is the heat that the water gets is going to be equal to the heat that the steel gives. And so then here in this box, we have a bunch of information. We have the heat capacity of the water, heat capacity of liquid steel, of solid steel, the delta H of fusion for steel, and then the melting point of steel. So let's look at the specifics behind this. This looks like a pretty dense paragraph of a problem. So something that I do like to do is to underline things. So here we have 27 moles of steel, and its starting temperature is 2,700 degrees Celsius. So it's definitely a liquid because we're above its melting point. And then we pour that steel into 2.5 kilograms of ice cold water. So its initial temperature is going to be 0 degrees Celsius. And so after this is allowed to mix, we record the water's temperature to be 39.92 degrees Celsius. So then they're actually asking us how much heat the steel lose. Okay, and so I actually think that you guys can do this one on your own. So go ahead and pause me and, try starting it and see how it is. So go ahead and 3, 2, 1, pause. Okay, did you pause and try? Hopefully. Okay, so let's go ahead and look at it. The answer ends up being C for this problem. And what we're going to do is just figure out how much heat the water absorbed, because that's much easier to think about than considering all the phase changes and such that the steel would have to go through. We could do it that way, but it would be a 3-step process as compared to just a 1-step process for the water. So we're going to figure out how much water or heat the water absorbed using Q equals MC delta T. And if we look at this heat capacity value that we're given for water, we can see that in the units we have grams. So that tells me my amount that I multiply my heat capacity by, or the M, also needs to be in grams. So it's an easy conversion to get our kilograms into 2,500 grams. We have our M, our C. And then here we have our delta T. So the delta T just comes from the fact that we went from 0 degrees Celsius and ended up at 39.92 degrees Celsius. And with our delta T's, it doesn't matter if we have degrees Celsius or Kelvin, the difference ends up being the same. And so then when we multiply this out, it comes out to be about 419,000 joules, which is going to be the same as 419 kilojoules. So if this is the amount of heat that the water absorbed, that's telling us how many kilojoules of heat the steel gave off or lost. Okay, so let's go ahead and look at another example. Okay, so here we have another calorimetry problem where we're mixing together 50 mils of 1 molar HCl and 50 mils of 1.2 molar NaOH. We're going to have an acid-base neutralization reaction. And we monitor the temperature as they're allowed to react, and we see that it increases from 21 degrees Celsius to 27.5 degrees Celsius. And our goal is to figure out the delta H of reaction for this neutralization process in kilojoules per mole, and those moles are going to be moles of HCl. Okay, and so then they go on to give us some more information, like the total volume of the solution, the density of the solution, and then its specific heat or its heat capacity. Okay, so let's first just kind of orient ourselves with what's going on. Which of the following statements do you think is true? Okay, so if you thought that A was true, good work. That is the correct answer. Okay, we see the temperature increasing, which means heat must be leaving the reaction, and that heat then goes into our thermometer, causing an increase in temperature. B, if the reaction were to absorb heat from the water, then we would see the temperature of the water go down, and that would be an endothermic process. And then C is also describing an endothermic process because it says the products would be at a higher energy than the reactants. So if we were to draw, our diagram where we have our products above as it describes and our reactants below, then we would have to put in delta H, and this would be a positive, be endothermic. Okay. So as we mentioned previously, we're going to treat the water as a surrounding. It's true that some water is given off in a neutralization reaction. That's going to be a really, really small amount compared to the water that's just acting as a source of support, kind of holding those molecules, the HCl and the NaOH molecules, in solution. Okay, so we're trying to figure out the delta H of the reaction. Here's our general approach. We're going to write a balanced reaction. It's usually a very good place to start. And then we're going to figure out how much of our reactants we have to work with. So it's going to be, when we figure out how many moles we have. Then we're going to figure out how much heat is transferred. How much heat is the reaction actually giving off? And we're going to do that by keeping track of how the solution's temperature has changed, given its specific heat and how much of it we have. And then once we know how much heat has been given off, we're going to figure out the delta H of that reaction by dividing per mole of reactants. Okay, and so in this case, we said we're going to write it per mole of HCl. Okay, so let's go ahead and start with this first part. So here we have our neutralization reaction. And it's already balanced. Everything in this case happens to be 1 to 1 to 1 to 1. And so we're going to find the moles of each reactant by using their volumes and concentrations. So we can take our 50 mils of HCl, convert that to liters, and then use the molarity to see we'll get 1 mole of HCl for every 1 liter of solution. Milliliters cancels, liters cancels. We'll see we have 0.05 moles of HCl to begin. And we can start for the NaOH with our 50 mils again, convert that to liters, and then we'll use our 1.2 molar NaOH to calculate the 0.06 moles of NaOH that we have. And we can again see mils cancel, liters cancel. And so from there, we're going to determine which is our limiting reagent. So we have this many moles of HCl that we found up here. And we're going to see how much of a given product each of our reactants could give us. So HCl is able to give us 0.05 moles of water, whereas NaOH is able to give us 0.06 moles of water. So we can see that HCl is our limiting reagent, and that's part of the reason why we want to write our delta H reaction in terms of HCl. Because HCl then is going to be what determines how much of our reaction has happened and how much heat then is due to that specific amount of reaction. Okay, so we've completed our first part. We have our balanced reaction and we know how much HCl is going to react. So now we're going to move on to where we determine how much heat was given off in this process using the Q equals MC delta T equation. So the C was given in the problem here. So that's how many joules it takes to change our solution by 1 Kelvin. So now we need our mass of solution. So we're going to use the volume that we have and the density to convert from the domain of volume to mass. We'll have our 100 mils times our 1 gram per mil, mils cancels. We see that we have 100 grams of solution. And then we can figure out our delta T by just comparing our final and initial temperatures. And as I mentioned before, it doesn't matter if we have our delta T in degrees Celsius or Kelvin, they'll end up being the same. So it's kind of nice, this is the one time where we can be a little bit lazy with our temperature units. And then we can take these 3 terms and set up our Q equals MC delta T expression. And solve. So this is the amount of heat given off by the reaction. And this is going to be specific to the amount of heat given off for this particular amount of our limiting reagent, which we said before was HCl. And so that brings us to our final step, where we figure out the amount of heat given off by the system by recognizing that it's going to be the opposite sign from what the surrounding is absorbed. And then we're going to take that value and divide it by our moles of delta or of HCl. And we end up with this negative 54,340 joules per mole of HCl, which is the same as about negative 54 kilojoules per mole of HCl. And this final computation we can also sort of relate to another equation that we might remember from our previous discussion of heat, which is that Q equals N delta H. And so what we have here instead is that delta H then equals Q over N. But then we can kind of evaluate whether this final value makes sense. And so we said initially that this is going to be an exothermic reaction because the temperature of the surroundings increased. And here we can see that we have a negative delta H, which corresponds to an exothermic reaction. So this seems reasonable, this seems good. So now let's look at another type of calorimetry problem. And here, instead of determining the delta H of a reaction, what we're going to do, say if we have this much of our initial species, and we put it in this much water, initially at this temperature, and we know its heat capacity, then what is the final temperature of our solution? Okay, so we're going to solve for delta T rather than solving for delta H. Okay, and so go ahead and practice this. So go ahead and pause me. Okay, good work pausing and practicing this problem. Let's go ahead and look at it together. So usually if you're unsure of where to start, converting your amount of reactant to moles is always a good place to start. But we said that usually our first step is determining our balanced reaction, which we were given. And so our next step is to figure out how much of our reactants we have in terms of moles. So we can take our starting amount, divide it by its molecular weight. Grams will cancel. And we'll see that we have 0.3088 moles of this ammonium nitrate. And so we can go ahead and determine how much heat this amount of ammonium nitrate would give off via this reaction. So we're going to do that by combining the amount of it we have with the delta H for its reaction. So we have our Q equals N delta H expression. And here we can see that we were careful to make sure that we divided by the coefficient associated with ammonium nitrate. So we're keeping in mind that this delta H corresponds to 1 turn of this reaction, and every 1 turn of this reaction we have 1 mole of ammonium nitrate that's used. And so we get this many kilojoules that this reaction would absorb. And so now that we know how much heat is being involved in this reaction and how much heat the ammonium nitrate is taking in, we can see how much that would affect the temperature of the entire solution. And so we can see that this is how much heat the ammonium nitrate would take in. And so the opposite is how much energy then the water would lose. And so then we can set up our Q equals MC delta T expression. This is the Q that we found using the delta H and the amount of ammonium nitrate. This heat capacity is given. And now we need to figure out what our mass is. So we're just going to add the mass of our two components together. And we see that we have 189.7 grams. And so we have our Q, we have our C, we have our M. And so we're going to solve for delta T. So here we have our Q equals MC delta T expression set up. And then the delta T that we would solve for is negative 10.44 kilojoules. So this negative 10.44 kilojoules makes sense because we see that we have an endothermic reaction. It's taking heat from the solution, and so the solution should get colder. But this isn't our final answer. Our final answer then is combining our initial temperature with the change. And so we can see then that our final temperature is going to be 11.2 degrees Celsius. And so on that note, I hope that you all are able to get some good practice in with both your limiting reagent ideas and your calorimetry ideas, and also get some practice rearranging smaller equations to determine the delta H of other equations using Hess's law. And so then on Wednesday, we'll talk about 2 other ways to determine the delta H of a reaction. I hope that you all have a great start to your week, and I will talk to you soon.